So, we will see some examples next. So, if the signal z of t is equal to sine omega t, what is its Fourier series coefficient? Of course, we know that this is periodic and we also know the fundamental period. So, what is the fundamental period? Fundamental period is 2 pi by omega. Fundamental frequency is omega. Of course, there are no other harmonics present in this. So, how to find out the Fourier series coefficient? So, z of t is a k e power j k omega t, and we need to find out these a k's. So, a k is 1 by t integral sine omega t e power minus j k omega t. Alright. So, we know that you can decompose this sine omega t as e power j omega t minus e power minus j omega t. We can let 2j outside. Okay. Multiply with e power minus j k omega t dt. So, this is e power j omega t of 1 minus k dt minus one plus k. Now, what is this integral? We know that this integral is equal to 0 if this k is not equal to 1. Okay, why is that? Because this is the area under the sinusoid, the complex sinusoid e power j omega t times some constant in one time interval. So, in one time interval you can decompose this as cos theta plus j sin theta, and within the one time interval the area of the cos becomes 0 and the area of the sin becomes 0. So, the entire area is 0. So, this will be non-zero only when the frequency is 0, that is omega t times 1 minus k is 0, and if it is 0, what does it mean? The entire value for k equal to 1 is equal to t, because e power j 0 is 1, you integrate it over t, you get the value to be equal to t. Okay. And similarly, what do you get here? So, this is equal to 0 when k not equal to minus 1 and equal to t when k is equal to minus 1. So, whenever k is equal to not 1 or minus 1, then this entire integral goes to 0. So, from this we can write what the Fourier series coefficients are. A k is equal to, when k is equal to 1, you get this term is 0, the second term is 0. So, when k is equal to 1, the first term gives you capital T, which the denominator gets cancelled out, and you have only 1 by 2j. So, you have 1 by 2j when k is equal to 1. When k is equal to minus 1, what do we have here? So, we have the same thing, you get capital T for this second integral, the first integral is 0. So, you have a minus sign here, right. So, there is a minus 1 times 1 by 2j. So, that is what you get for k is equal to 1 or minus 1. For all other cases, the entire integral is 0. So, this is put back here to get the Fourier series representation. Substituting this, you get a minus 1 e power minus j omega t plus a 1 e power j omega. This is a Fourier series representation. In other words, this is 1 by 2j minus e power j omega t plus e power j omega t. This is something that we already knew and used. So, we have computed this in a roundabout fashion. But this tells us a nice thing, because if you already know the representation of something in the complex sinusoids, you don't have to do this entire computation. So just by looking at this, you can say that, okay, I know that this is k is equal to -1, this is k is equal to +1. So the corresponding ak from this decomposition itself, directly you can write has to be -1 2j for k is equal to -1 and should be equal to 1 by 2j for k is equal to +1. So you don't have to do this entire computation. This is just something that is done to show that you will get the same thing. Whenever you have a signal, and if you can directly represent that in terms of, these eigenfunctions. So in this case, I am not going to do this entire thing for cos omega t. So because we know that cos omega t can be decomposed like this. So if I can decompose cos omega t like this, then what is the corresponding Fourier series coefficients for cos omega t? The corresponding Fourier series coefficients for cos omega t is straightforward. It is ak equal to 1 by 2 for k is equal to -1 or 1, 0 elsewhere. Okay, it's as simple as that. You don't have to do this entire integration. For sin omega t, it is just -1 by 2j or 1 by 2j. For cos omega t, it is just 1 by 2. What about e power j omega t? So if the signal itself is e power j omega t, then you know obviously that ak is equal to 1 for k is equal to 1, 0 elsewhere. So this is if the fundamental frequency is omega. If the fundamental frequency is something else, then the AKs will change accordingly. For example, what is the Fourier series representation of e power j omega t when the fundamental frequency is, let us say, omega by 2? So for fundamental frequency of omega, e power j omega t has a Fourier series representation or the Fourier coefficients which are given by 1 for k is equal to 1, 0 elsewhere. Now what if the fundamental frequency is omega by 2? Then e power j omega t will have Fourier series coefficients given by 1 for k is equal to 2, 0 else. Now why is this true? So remember that the Fourier series coefficient is simply summation ak e power j k omega f t, where f is the fundamental frequency. Okay, so if omega f is equal to omega, then this entire expression simplifies to just be k omega t. Then you can get the Fourier series coefficient of, like, if this is equal to e power j omega t, then it simply means that you will get that when k is equal to 1 and a1 is equal to 1. Now what if the fundamental frequency is omega by 2? Then the Fourier series representation is ak e power j k omega by 2 t. Then this will be equal to e power j omega t for k is equal to 2 and a2 is equal to 1. Okay. So the Fourier series representation can change depending upon what is your fundamental frequency. Remember, this is what we saw in the case of time scaling and all, right? So the Fourier series representation can be different depending upon what is the fundamental frequency. So the same signal e power j omega t can have different Fourier series coefficients depending upon what is the fundamental frequency that is chosen, but the Parseval's theorem will still hold. No matter what is the fundamental frequency, when you just find out the magnitude squared of all these Fourier series coefficients and add up, it will equal to the power of the signal. So that is still true. It does not really matter what is the fundamental frequency. And for the sinusoids, it is so easy to find out the Fourier series. All you have to do is just decompose in terms of the complex exponentials and just get their corresponding coefficient. Okay, let us solve another interesting example. So in this example, what is asked is to find out the Fourier series of an impulse train. So what is the impulse train? Here it says that at t is equal to 0, you have an impulse, a unit impulse. Okay, so this is 0, and after capital T seconds, you have another impulse, and before capital T seconds, because this n is equal to minus infinity to infinity. So basically, you have delta of t plus delta of t minus t plus delta of t plus t plus delta of t minus 2t and so on. So, you have just a train of impulses for every t seconds. This is minus t, this is t and this is 2t. So, this is our input signal. So, if this is our input signal, clearly this is periodic and it has period t, capital T. So, can we find the Fourier series coefficient for this? Yes, of course we can, and let us see how to find this. So, z of t is equal to summation a k e power j k omega t, and what is our omega here? The choice of omega is the fundamental period gives the choice of omega. So, it is 2 pi by t, and a k is 1 by capital T integral z of t e power minus j k omega t. Okay. So, in this integral, so let us say we are going to integrate this from minus t by 2 to plus t by 2. So, from minus t by 2 to plus t by 2, the signal has nothing but only one impulse. So, this entire thing is in fact equal to integral delta of t e power minus j k omega t dt. So, there is nothing else in this interval other than this Dirac delta function. So, life becomes simple. So, this is nothing but e power minus j k omega times 0, which is nothing but 1, and you have this constant. So, 1 by t. So, a k is 1 by t. In other words, the Fourier series coefficient tell us that the signal could be represented as 1 by t e power j k omega t. So, what this tells us is an impulse train has all frequencies which are harmonics of the fundamental. It has infinitely many frequencies. So, the coefficient is 1 by t for all. In other words, you can write this as, so 1 by t from this relationship you can say that is equal to omega by 2 pi, right. So, if I have an impulse train which has a frequency omega, then it means that for all frequencies from minus infinity to plus infinity, all of these complex sinusoids are present inside this impulse train. So, it has infinitely many frequencies, and the component of all of these frequencies is exactly the same. It is equal to omega by 2 pi, or which is equal to 1 by t for all k. So, if I have to plot this, let us say I plot this as k, then what I get is something like this. Okay. This is 1 by t and this is 1. So, this is the Fourier series representation or the Fourier coefficient representation. I can also represent this as k omega. So, if we represent this as k omega, what do we get? We still get the same thing. All the magnitudes are 1 by t still. Now, what is the gap between them? So, this is 0, this is omega, this is 2 omega, this is 3, so this is minus omega, minus 2 omega and so on. So, the gap between them is exactly equal to the fundamental frequency. So, an impulse train actually produces another train in the Fourier series representation. So, this is very interesting. All it says is there are infinitely many frequencies. So, we have a signal here which has infinitely many frequency components from minus infinity to plus infinity, and their magnitude is all the same, which is equal to 1 by t. Now, this is a very interesting signal. So, it's very difficult to get such a signal in practice first of all, but this can help us represent many things in real life. So, if we take, let us say, a rectangular signal. Now, how can I convert a rectangular signal into a rectangular pulse? So, what is a rectangular signal? A rectangular signal we know is just this, right. So, from minus half to plus half, you just have 1. This is a rectangular signal. This is not periodic, but if I want to convert this into a rectangular wave, so what is a rectangular wave? Which is something that is periodic. How do I convert this rectangular signal into a rectangular, let me call this x of t and let me call this y of t. Now, if I want to convert this into a periodic signal, okay, a periodic signal where this is 0, let us say this is capital T, this is minus t. This impulse train actually helps us to convert this rectangular signal into a periodic signal. How does that work? So, if we simply convolve this x of t with this impulse train, what happens? So, this is a very nice representational trick. So, anything that we know in only one period, in only one cycle, we can represent that as a signal and then simply convolve that with an impulse train to produce a periodic signal, right. So, which means if you know some signal, you can always convert it into a periodic signal by convolving that with the impulse train. So, if you convolve this with the impulse train, again you can use the properties of convolution, the distributivity and linearity, and you can say that the output is now nothing but infinity x of t convolved with, once again use the properties of convolution, with some delta which is shifted by some time. We know that the output is now n is equal to minus infinity to infinity x of t minus n t. What does this tell? It tells us that for n is equal to 0, you get x of t, the same signal as such. For n is equal to 1, you get x of t minus t. So, you shift it by t. Okay. So, this is t plus half, this is t minus half. For n is equal to minus 1, you get x of t plus t. So, you shift it to the left. And so on. So, what we have done effectively here is that just by convolving this signal x of t, which is time limited, it is limited in time, okay, with a train of impulses, we have converted that into a periodic signal. So, this becomes very useful for us in several analyses. Another thing to note is that if the length of this time limited signal is some t naught, then the period of the impulse train should be greater than this t naught. Only then there won't be any overlap here, otherwise there will be an overlap. So, this is what you should note when you use this representation. Recall that we started out a lot of analysis and motivated that through RC circuit. So, let us say we have an RC circuit, something like this, and we had an voltage source. Okay. So, this is the voltage source. Let us say it is a time varying function, and this is the voltage across the capacitor, and this is the voltage across the resistor. So, from Kirchhoff's law, we said that V as t is equal to V R of t plus V C of t, and we were able to derive the impulse response of the system when the input is the source voltage and the output is the voltage across the capacitor, and we found that the impulse response is given by this signal. Okay. Now, can we try and identify the frequency response of the system, try to see what happens to the system, and from this frequency response, can we try and identify is this a low pass filter or a high pass filter, how does it really behave? Okay. So, we can get that insight just by looking at the system. So, earlier we derived this impulse response from the techniques that we found out earlier by modeling the input and output and then taking the derivative, and then from the derivative we were able to find out the impulse response. So, once we have the impulse response, remember how to find out the frequency response. The frequency response is the eigenvalue. The eigenvalue is nothing but h of t e power minus j omega t. It's the inner product, remember. So, that's what we're trying to do here. So, in this case, just plug in, you get 0 to minus infinity. This is u of t. So, just substituting, you get this. The u of t makes this integration from 0 to infinity. Then you get e power minus t e power j omega t dt, which is equal to e power minus j omega which is equal to e power t of minus t of 1 plus j omega divided by 1 plus j omega 0 and infinity. Okay. So, this is equal to 1 by 1 plus j omega. When you substitute infinity, you get just 0, and when you substitute 0, you get 1 by 1 plus j omega, and this minus gets cancelled. So, you have 1 by 1 plus j omega. This is our eigenvalue. From this eigenvalue, we can find out what the frequency response will look like. So, you plot this as a function of omega. So, what happens when omega is close to 0? So, when omega is close to 0, you get 1 by 1. So, for very low frequency, you get something like this. So, this is just 1. Okay, at 0, you get 1. And what happens when omega is close to infinity? When omega is close to infinity, this is 1 by infinity form, which goes to 0. Okay. So, this is how the frequency response looks like. So, as omega tends to infinity, you get lambda omega going to 0, and as omega goes to 0, you get lambda omega equal to 1. So, for low frequencies, the output is just as such, no attenuation, nothing. For high frequencies, there is a very, very high attenuation. So, that is what the output is, which makes sense because the capacitor behaves like a short circuit for high frequencies. Because it behaves like a short circuit, you find the voltage across this, it is almost 0. And when it is an open circuit, then you find the input voltage to be directly coming output at the output, right. So, that is exactly what this is telling us also. So, the output is exactly equal to the input, like there is no attenuation or whatsoever when the input is a DC signal. Okay, the frequency response is 1 and the input signal is DC. When the input is an AC, then the capacitor starts behaving like a short circuit, and it behaves like a short circuit only for very high frequency of AC signal, not for any arbitrary AC signal, for very high frequency of AC signal, and the output now almost becomes 0 because it is like a short circuit. So, this intuition also now works very well from our analysis. So, we got to this frequency response only by looking at the impulse response. So, if we did not know the impulse response, this eigenvalue would have been difficult to compute. But because of this eigenfunction eigenvalue theory, we can find the eigenvalues in this case very easily. Like we did not even have to go through all these complicated way of deriving this impulse response, and then from there the eigenvalues. So, look at this equation. From this equation, we know that let us say the input was some x of t, then the output is some y of t, then we know from earlier, so this is, let's say, some R, this is some C, then RC times dy by dt is what this voltage is, because of course we know the relationship between the current and this output. So let us say the input was a complex sinusoid. If we know the input output relationship for one complex sinusoid, that is enough, because if we know that, we can just simply replace omega for different values, and if I know the input output relationship for this, it is enough, because I can express any of my input signal as a summation of this sinusoid. And once I know this input output relation, let's say I know the output of e power j omega t, let us say that it is some y1 of t, or let us say it is y omega of t, because depending upon the frequency the output can change. Then I can know the output for any periodic signal. Why is that? Because any periodic signal I can write it as some ak e power jk omega t. So that is the input now. Then what is the corresponding output? Because of linearity, because of this LTI nature, I can say that the output is now ak yk omega t. I know that the output of this system for j omega t is y omega t. So all I am doing here is a superposition of several e power j omega t's for different values of this frequency. So the output should also be superposition of the corresponding outputs. That is exactly what we have written here. So if we know this one relationship, we can find out the output for any possible periodic input. Okay. So let us find this out. So if the input is e power j omega t, what is the output going to be? Now the output is also very easy to identify, because the input here is an eigenfunction of LTI systems. E power j omega t is an eigenfunction of an LTI system. What does that mean? It means the output is going to be some scaled version of the input itself. That's all the output is going to be. So this is now even simpler to solve. So what is this expression? It is d by dt of this entire term, which is nothing but lambda omega times j omega e power j omega t. Okay. So now if we want to find out the eigenvalues, it's quite simple. So just divide both the sides by e power j omega t, then you get 1 so lambda omega is 1 divided by 1 plus RC j omega, which is what we got here, So instead of going through this entire analysis of finding the impulse response, from there computing the eigenvalue, we used some interesting properties here. What is the property that we used? We said that we will consider only a complex sinusoid to be the input, and if that is the input, because of the eigenfunction property, the output has to be of this form, and by plugging in that, we found out the eigenvalue. So the frequency response of this circuit we identified without much analysis at all. So this is the advantage of learning signals and systems, right? So we learnt a lot of complex things, we learnt a lot of complicated things, and we built one on top of the other, and finally we understood that this relationship is true. And from this, what we now have done is we have gotten to a point where we found the frequency response of this circuit without much effort. We just wrote this equation and we said that I know that this is LTI. I can check and verify that this is LTI. The moment I am able to say that this is an LTI, I will use the eigenvalue eigenfunction property and I will just write down this. And if I write down this, from this I am able to find out the eigenvalues. So if I find the eigenvalues, I know the frequency response. I can draw the frequency response. The moment I am able to draw the frequency response, I can clearly tell how this circuit is going to behave. If I feed in a DC, the output is exactly the same signal. If I feed in high voltage or high frequency AC, the output is going to be completely attenuated. So we can completely understand this circuit just by doing this frequency response computation. And this becomes a very, very important tool in circuit analysis, where often we would end up computing the frequency response of any circuit, and from that we will completely characterize this circuit. And for that, Fourier analysis becomes very important, because once we know this, what happens if I feed in a different signal? I know that I can decompose my periodic signal in terms of e power j omega t's, and I know what the output is going to be, because now I know this eigenvalues also. I simply will multiply the eigenvalues with the Fourier series coefficients of my input, and I know the output. So I know the system completely, I know its frequency response, and I have characterized this fully. So all what we have learnt becomes very useful in circuit analysis.